All right, today we're cracking open the engineering playbook. I'm talking about the rule book for everything from the power grid right down to the microchips in your pocket. We're diving into the 4 fundamental equations that govern all of electricity, all of magnetism, and even light itself. And look, these aren't just some abstract physics concepts. You should think of them as the core operating system for all of modern electrical engineering.
So let's just jump right in with a real-world question. Picture the incredible power of, say, an electric locomotive or maybe a high-performance EV. Every single watt of power that's controlled in its traction motor, every single bit of energy that gets regenerated during braking, all of it is described perfectly by the 4 equations we're about to break down right now.
Okay, so here's our game plan. First, we got to get the language down, the language of fields. Then we'll tackle the equations in pairs. We'll start with Gauss's law for static fields, then move to Faraday's law and induction. After that, the Ampère-Maxwell Law, the great unifier. And finally, we'll put it all together to see how these equations lead to something, well, truly universal.
Right. Before we can even begin to read this playbook, we need to understand the language it's written in, and that language is vector calculus. We're going to focus on 2 really key operators that tell us exactly how fields behave at any single point in space. They're called divergence and curl.
First up, let's talk about divergence. Okay, just imagine for a second that a vector field is like the flow of water. Divergence tells you if, at any given point, there's a source, like a hidden water pump, pushing fluid out, that would be positive divergence. Or maybe there's a sink, like a drain, pulling fluid in, that's negative divergence. It's just a single number, a scalar, that gives you the net outward flow from that one specific spot. All right, next up is curl, and we're going to stick with our water analogy here. Imagine you drop a tiny little paddle wheel into the stream right at one specific point. Now, if the water flowing past makes that paddle wheel spin, boom, the field has a non-zero curl right there. And the curl itself is a vector. Its length tells you how fast the wheel is spinning, and its direction points along the axis of that spin. It's basically a measure of the local swirl in the field. Okay, so now we have our language tools, divergence and curl. Let's tackle the first 2 equations. Now, these guys describe how electric and magnetic fields behave when everything is completely static, nothing is changing over time. Think of these as the foundational ground rules. So here it is, Gauss's law for electricity. Let's look at the differential form first. This is the microscopic rule. It says that the divergence of the electric field, well, it's equal to the charge density at that exact same point. To put it simply, electric charge is the source of the electric field. Where you have charge, you have a field diverging from it. Now, the integral form is the big picture consequence of that. It says if you draw any closed surface, the total electric flux flowing out of it is exactly equal to the total charge you've trapped inside.
The integral form becomes really intuitive with an analogy. So picture a running engine block sitting inside a totally sealed room. The total amount of heat escaping through the walls, it doesn't matter if the room is a cube or a sphere or some weird shape. It only depends on how much heat the engine itself is putting out. And that is exactly what Gauss's law is saying. The total electric flux only cares about the source, the charge that you've enclosed.
And this visual just illustrates the differential form perfectly. A single positive charge acts like a tiny microscopic pressure source, like a tiny pump. You can see the electric field lines diverging or flowing straight out from it. This simple local rule, happening at every single point where there's charge, is what all adds up to create that big picture macroscopic effect we just talked about with the integral law.
Okay, now let's switch over to the magnetic side of things. And right away, you should notice something profound. This is Gauss's law for magnetism. And look, both the differential and the integral forms are equal to 0. The divergence of the magnetic field is always 0, everywhere, no exceptions. So what does that mean? The crucial takeaway is this: there are no magnetic monopoles. No magnetic charges. It means that unlike electric fields, which can start on a positive charge and end on a negative one, magnetic field lines have no beginning and no end. They must always form closed loops. A great analogy is a sealed hydraulic system. The fluid just circulates around and around, endlessly. There's no single source point, and there's no drain. That is the fundamental truth about magnetism that this simple equation tells us. All right. We are now leaving the static world behind and entering the dynamic one. And trust me, this is where things get really interesting. This is where the fields finally start to talk to each other, to interact. And the first rule of that conversation is Faraday's law of induction. Faraday's law. I mean, this is the heart and soul of every generator, every motor, every transformer on the planet. Just look at the differential form. It says the curl of the electric field is tied directly to how the magnetic field is changing over time. Think about what that means. A changing magnetic field literally creates a swirling, curling electric field out of nothing. This is an E field that forms closed loops, totally different from the static fields we saw earlier. This right here, this is the engine of electromagnetism. And you want to see that engine at work? Let's look at a really high-power example, regenerative braking. Okay, so when an EV, or an electric train, starts to brake, its momentum keeps the motor spinning, right? Well, that rotation causes the magnetic flux inside the stator coils to change, and change fast. And that's when Faraday's law just kicks right in. That changing magnetic field induces a curling electric field in the coils, and that E field is what drives a huge current backwards into the battery or the grid. It recharges the system and, at the same time, creates the braking force that slows the vehicle down. That's Faraday's law in action, pure and simple.
Okay, so we've just seen that a changing magnetic field creates an electric field. So the natural question is, does it work the other way around? Can a changing electric field create a magnetic one? Now, Ampere's original law said no, only moving electric charges, a current, could create a magnetic field. But the great James Clerk Maxwell saw a flaw, a missing piece to the puzzle. And adding that one little piece would unify the entire theory and lead to one of the most incredible predictions in the history of science.
And here it is, the complete Ampère-Maxwell Law. It tells us that a curling magnetic field is created by two possible things. The first term, J, well, that's just your standard current, the flow of electrons. We knew about that. But the second term, that was Maxwell's stroke of genius. He called it displacement current. And what it means is that a changing electric field all by itself can also create a curling magnetic field, behaving just as if it were a real current.
So, why do we even need this? Well, think about a capacitor, maybe one in a big traction inverter. The actual flow of electrons, the conduction current, literally screeches to a halt at the insulating gap between the plates it can't cross. So, according to the old law, the magnetic field around the wire should just disappear in that gap. But experiments show it doesn't. Maxwell realized that the rapidly changing electric field inside that gap acts like a ghost current, if you will, the displacement current. And it's what ensures the magnetic field continues on its way uninterrupted. It was the absolute final piece of the puzzle.
Okay, we now have all four equations on the table. We've gone through the static rules, we've gone through the dynamic interactions. Now, let's put them all together and see the magic happen. This is the grand synthesis.
So, let's recap. Piece 1. From Faraday's law, a changing magnetic field creates a curling electric field. Piece 2 from the Ampère-Maxwell Law, a changing electric field creates a curling magnetic field. Do you see it? Do you see the feedback loop we just created? A changing magnetic field makes an electric field. But that new electric field is itself changing, so it makes a new magnetic field, which in turn makes a new electric field. And it goes on and on and on. It's this beautiful, self-sustaining dance. And at a certain point, this dance doesn't even need the original charges that started it. It just detaches and travels through space on its own. It propagates as an electromagnetic wave. It is light. It's radio. It's Wi-Fi. It's all of it.
And there you have it. 4 equations, a complete self-contained playbook for pretty much the entire macroscopic world of electricity and magnetism. It's an incredible achievement. But of course, this perfect classical picture isn't the final word. What happens when you zoom way, way in? What happens at the smallest scales, where these smooth, continuous fields we've been talking about give way to discrete little packets of energy called photons? Well, that's where these classical laws meet the quantum realm. And that, my friends, opens up a whole new playbook.